We Can you hear me okay online?
Yeah.
Perfect, thank you. We're just waiting for some more people to come on. Right, okay, you should be able to see my slides now. I've waited for long enough. So we were looking at orthopedic uses of polymers, but first we're going through the different kind of domains of bone. We'll certainly have a look at the different mechanical properties of bone, and then we'll get towards a section where we talk about the replacement of kind of hip joints and things like that using polymers. And you may remember parts of that from when we were in our kind of first sets of lectures where we talked about kind of coating the ball joints in ceramics and replacing those ceramics with things such as ultra high molecular weight polyethylene. So we'll kind of get to that as we move along. But first we'll define these things and do some kind of mechanical interpretations of them. So there's two major types of bone tissue. There's cancellous bone or trabecular bone or spongy bone, which is made up of individual trabeculae, and they have a relatively low elastic modulus, but the structural morphology of those the trabeculae can define the structural stiffness of the cancellous bone. And then we also have cortical bone or compact bone, and that makes up for about 80% of the skeletal mass. The elastic modulus is higher, 17 to 24 GPa. And this forms a protective outer shell around every bone in the body. So it has a slow turnover rate and high resistance to bending and torsion. So it's very rigid. But it provides strength where bending would be undesirable, such as the middle of long bones. So long bones, by their very definition, are longer than they are wide. So you can see a breakdown of cortical bone on this outside edge. And then we can see the trabecular bone, which almost looks like some kind of porous membrane in the middle. And if you are a non-vegetarian and you go to Texas Roadhouse, you can see it in your T-bone steaks as well. So, you know, if you go with your parents or something, you take a bit of time out to look at your T-bone steak, you'll be able to find out the different regions in that. So you can see in the center of that T-bone, you have the trabecular bone, and then you have the cortical bone around the outside edge there. So you can learn something from eating out. So bones exhibit anisotropic behavior, and it's anisotropic because the strength of the bone depends on whether we load it through tension or compression, and whether the load is applied longitudinally or transversely in the bone. So the bone, as we see before, is made up of these osteons. They are cylindrical structures that form the fundamental functional units of compact bone. Due to the relative orientation of the osteons to the applied mode is what affects the anisotropic behavior there. So so for example, when we're looking at the cortical bone, it's stronger in compression than tension. So the strength of compression is about 100 to 230 pascals there, and the strength in tension is less than that. So in compression, there is a percentage elongation around 3%, regardless of if the load is applied longitudinal or transverse. Longitudinal or transverse we'll go through in the next slide here. So you can see if the cortical bone is loaded transversely in tension, so it's longitudinally applied there. The modulus strength and the percentage elongation at break, the strain to failure is reduced. So this is the longitudinal. That's definitely, it's not longitudinal, that is longitudinal. I have a habit of doing the L's on H's. And this one is transversely. So that's really the difference in those applied forces and the percentage elongation and strength of the brake or the strain to failure is because of the orientation of those oscions in the bone. So we can see that the tensile strength and the percentage elongation at break of cortical bone from the human femur changes as a function of age. So you will see that between the ages around about 30, actually, you get the most tensile strength in there. You get the highest percentage elongation at break in there. So you're kind of at the optimum when you're approaching 30. Before 30, you're still trying to build up the bone, and the bone's still trying to mature. And after 40, you start to undergo things such as osteoporosis, kind of the breakdown of that bone tissue there. So the bone tissue, as we know, is stronger in compression versus tension there. So we can see the difference in changes to do with age, which is fairly straightforward to understand. So there are a number of different hard connective tissues in the body. There's 3 types of cartilage. The first type is elastic cartilage, which is the ear and the nose. The second type is this fibrocartilage, which is found in the intervertebral space on meniscus. And TMJs, does anyone know what a TMJ is? No. Okay. Does anyone know where a TMJ is positioned? All right. Okay. Let me write it down. So TMJ is temporo. The TMJ is a temporomandibular joint. Does that give you a clue of where it might be positioned? Yeah.
Using your jaw.
Yeah, that's right. So that's the sliding hinge connecting the jawbone to the skull. And then we have articular cartilage, so that's articulating onto the ends of bones, and we'll kind of come back to this in a bit more detail later on, but it protects the underlying bone and a joint from abrasion and wear. If damaged, you can undergo trauma, and we all know about osteoarthritis and the pain that causes, and that occurs when the bone is exposed to different stress concentrations. So you get pain from the nerves in the bone that are exposed there. So when we're talking about articular cartilage composition, we have it separated into 2 sets of living cells. The first set of living cells is chondroblasts. And the second type is chondrocytes. So chondroblasts are immature versions of chondrocytes. Does anyone know the difference? Oh, it's kind of in there, but does anyone know the difference between chondroblasts and chondrocytes in respect to the extracellular matrix?
Chondroblasts are laying cartilage down, while chondrocytes are stuck in cartilage and yes, agreed in the matrix.
Yes. So is that what you was going to say as well? yeah, I'll take that one. So the chondroblasts are known to obviously secrete the extracellular matrix of the cartridges, so they kind of supply it, where the chondrocytes are these mature versions of the chondroblasts, which help to maintain the cartilage in there. So the extracellular matrix, and it's kind of what we've been trying to mimic with kind of some of the polymers we look at, is that they are consistent of collagen fibers. There's a type 2. They give the tissue structure and tensile strength, and they form around about 45%. Elastin fibers, which are kind of structural proteins, so they have tissue they give the tissue structure and elasticity. And then the proteoglycans that we talked about before, they resist compression. They serve as space fillers and provide hydrated space around cells. So this is a compound that's composed of a protein backbone. Sorry, I'm forgetting I've got to write in these things. Yeah, so it's composed of a protein backbone attached to long side chains of negatively charged glycosaminoglycans, GAGs, which are these long unbranched polysaccharide units. So there's a few examples there. And the rest of that extracellular matrix is made up of water. So about 70% of it is water in there. So here is an example of how the different water concentrations and the different collagen concentrations change depending on kind of which bone tissue or cartilage that we're looking at. So I'm going to give you a couple of minutes to have a look at that and have a think about why the cartilage contains more water. And also kind of why the percentage collagen is high in the tendons, ligaments, and the cartilage too, compared to the trabecular and cortical bone. So I'll give you a couple of minutes to have a look at that, and then we'll go through that. Okay, so you've had a few minutes to digest that. So can anyone offer an answer really why the percentage of water in cartilage is particularly high?
It's probably because of all the glycosaminoglycans, and they're very polar, so they can draw in a lot of water.
Yes, you are pretty much correct there. So the only thing I would add to that is that because of the content of the plastic glycans, they can act like sponges, which is exactly what you're saying, I suppose. So they, under compression, what happens is that some of the water is squeezed out of those cartilage sites in there. But because of that concentration of those GAG proteins in there, the prostaglycans, it can soak that water back up again. And that acts as kind of a way of modulating the impact that bone will feel. So what about percentage collagen? So let's start. Why are the tendons and ligaments got a high percentage collagen?
They need to be more like flexible and elastic compared to bone.
Yeah, you're correct. So one of the, actually, collagen itself is not that flexible. It does have its limits and it does fracture fairly easy, but it is more flexible than some of the other components that structural components we have in there. So by increasing that percentage collagen in the tendons, ligaments, and also the cartilages, you give it a degree of flexibility that the other trabecular bone and obviously the cortical bone, which is especially protecting the bone, doesn't need to have in there. So that's good. I need to work out to unlock my iPad for longer. So we've seen this before. We've seen how the different mechanical properties change depending if we're looking at soft tissues and hard tissues. And you've all seen these tables with the modulus tensile break and the strain break. So now we've got the addition of those hard tissues in there. So we can see that the cortical bone, which is a barrier to protect the bone, is much higher, has a much higher modulus and low flexibility, whereas the cartilage has more flexibility but a low modulus on there. So one of the important things that we were also talking about before, and we'll kind of move on to this, is that when we're trying to develop new polymers or new materials that are implantable or going to support bones, that we have to try and match up with the mechanical properties of the material we're trying to place or support. So this will become particularly important in the next few slides. So long bones, as we said before, the very definition of a long bone is that they are longer than they are wide. I don't know if that is an exact medical definition, but kind of makes sense. But at the ends of these long bones, they're covered with this articular cartilage, and you can find that on femurs, tibias, fibulas, humeri, radii, ulnars, phalanges, and toes. And the idea is that those articular cartilage on the end of those bones is meant to enable and protect the ends, so they're basically where the mobilization occurs. So bone tissue undergoes spontaneous regeneration and remodeling, and it's kind of the basis for some of the orthopedic regenerative medicines. But it's a balance between two different types of cells. It's the difference between, it's a balance between osteogenic, which is bone forming, and osteoclastic, which is bone removing processes. We're not going to go into this in very much detail, but Wolff's law is something that is applied to bone remodeling. So if we apply more stress, the equilibrium is shifted towards osteogenic activity, and if we apply less stress, the equilibrium is shifted towards osteoclastic activity. I'm starting to think the day doesn't matter. I just can't spell it anyway. Osteoclastic activity. So the goal of any fracture treatment, especially long-blown fracture treatment, is to stabilize the fracture. So we prevent motion between the fragments, and we can also allow regeneration and remodeling. So there is a few different types of treatments in there. So we can have non-surgical treatments, which are things such as a cast. But then we can have surgical treatments where we can use more biomaterials that we have at our disposal. So the surgical methods is that we can have external fracture fixation, So you don't actually open the fracture site. The bone fragments are held together by pins through the skin and structurally supported by external bars. They are a feat of engineering in themselves. If you've seen any of these kind of external pins that are used. And the other surgical intervention that you can have is these internal fracture fixations. So that's done with the open fracture site, and the bone fragments are held together by wires, screws, plates, or other devices in there. So here's some examples on the different x-rays. So on the left-hand side, we can see that for the long bone repair, the external fixation devices is exactly what it says on the tin. They are external to the limb or the bone or the long bone that they're trying to repair. Internally, you've all seen these things before. You can use nails and rods, bone plates, screws and pins. I actually was, when I was researching this topic, I don't know how, but I ended up on YouTube to seeing a process of someone putting a hip joint back in, and it was pretty brutal. It looked like they're actually fighting in the surgery room. But yeah, I mean, if you're that way inclined, I would check some out, because some of these surgeries are pretty hefty surgeries that they have to put in place there. So as we know, when we have a fractured bone, we have a loss of support function due to the break in there. Using things such as bone plates, which is shown here on the skull center here, restores continuity by compression of the bone fragments. It's referred to as plate osteosynthesis, and they are affixed in using screws. So they're used for places where casts can't be applied to the injured area. Obviously, the skull, you can't directly apply a cast to that. So things such as facial areas, they can also be used in femoral or other fractures too. So a bone plate material should exhibit a number of properties. So what kind of properties do you think a bone plate material should exhibit?
Maybe like a similar modulus to the bone.
Yes, you are. Yeah. All right. So it's adequate stiffness and strength, and then I'm just going to add another one in there. Okay, so I think that summarizes both of those. So you want adequate stiffness and strength, and then you want the required mechanical properties during the entire healing period. What other properties would we like of those bone plate materials?
Biocompatible.
Yeah, perfect. So biocompatibility.
I don't know if this is similar to that, but like if they're biodegradable, you don't have to go for a second surgery.
Yeah, so that one's not on my list, but that is a sensible one as well. So what about stress relaxation and creep? Is that something that we would want in these things, or is that something we would want to avoid?
We want to avoid the shrinkage.
Yes, correct. So no stress relaxation or creep. And then the last one and I'm going to give you this one, is that we don't want any brittle behavior. So we want some toughness and ductility, but we don't want to exhibit non-brittle behavior.
Can you explain why we don't want stress relaxation or creep?
So we obviously don't want them to change the, we don't want the material to elongate, right? We want it to be in a fixed position. And so we don't want it to change over time. Does that make sense?
That does, thank you.
Uh-huh. Yeah, so as those bones are in, as those plates are in place and they have initially adapted, we don't want them to lose the properties over time. So incurring stress, relaxation, or creep will mean that they would change and we would lose the force that we're applying on those particular areas. Okay, cool. So when we're looking at using metals in particular to replace or modify the different areas of cortical and cancellous bone, we have a little bit of an issue. So what is the immediate issue highlighted on this slide?
Modulus.
Yeah, so okay. So the modulus of the metal implants is much higher than the elastic modulus of the cortical bone in there. Now, the problem with this is that you can give rise to stress shielding or osteopenia. So that's caused by stress shielding, but it's when we have a reduced bone mass. So when we remove the normal stress from the bone using an implant, so when we have a metal fixation device that carries too large a portion of the bone's load, the bone will not regenerate properly, and that's because we have this mechanical mismatch between the modulus of the metal fixation and the bone itself. So we can see that, and again, here's a favorite table. We can see that certainly the cortical bone, as we saw previously, has a much lower modulus than the metal itself. Yeah. Yes. Yeah. So yeah, the question is osteopenia because the bone is in direct contact with the metal support, which means that it can't regenerate its strength and it can't regenerate structural composition back again. And yeah, that's correct, right? So if we put too large a support in there, osteopenia is a result of that. So that's where polymers become interesting, right? Because now we can start to match these polymers up to different types of materials and different elastic modulus of materials here. So here's one example. So example here is PEEK, or polyaryl ether ketone, which is this structure here. As normal, we give you all the glass transition temperatures, and this is semi-crystalline. It exhibits a high modulus, high wear strength, and degradation resistance in there too. And actually, one of the interesting things for those of you who have kind of ventured into the area is that PEEK is actually possible you can 3D print PEEK as well. So when we're talking about personalized medicine and we're talking about, shaping different replacements for particular people, we can 3D print those things. So we have a good control over the resolution and the shape of those things. Now, PEEK itself has a relatively low elastic modulus of around about 4 GPa. But what we can do is that we can put carbon fiber or put chopped carbon fiber into the kind of PEEK material. So if we have 30% weight to weight of this carbon fiber, we can actually increase the elastic modulus to around about 20. And now you'll notice that compared to the annealed titanium supports, which is 114, we're actually closer with 20 to that of the cortical bone. So what we're seeing now is that even with bone, we can start to use polymers as a support or as a support in those cases. Now there is a few other examples on here as well. So one is PPES, the other is PPS, and then we also have PES and PBPS. And so all you really need to know with these things is that they can also be used to match up to different portions of the bone. And you'll see the examples here with the PPS and the PES is that they have a similar elastic modulus as a cancellous bone. But we can also play around with the different elongation at break. And you know now that when we synthesize these different polymers, we can synthesize them as block copolymers or random copolymers, so we can modify those different properties in there. But it's just to show that the polymers can be used as replacements for metals in these different circumstances. So total joint replacement. So when we're talking about joint degradation, we're talking about the loss or destruction of the articular cartilage. And that can be through disease, so osteoarthritis, or it can be through severe injury and wear. So actually, if there's any athletes out there who like running and things like that, repeated motion like that can wear at your joints as well. So be careful. Don't run. No, don't. Keep running. Just be careful. And that can obviously cause severe pain, loss of motion, and sometimes you can get deformities in the joints there. So unlike the bone, the cartilage has very limited capacity for wear. So you can see on this image that articular cartilage covers the ends of the bones to form these smooth articular surface joints. And obviously there is a meniscus in between those things as well, which will help lubricate that joint. You can see on the top one, top image, we have that articular cartilage, which gives this very smooth surface. On the bottom bone, where we have degeneration of that articular cartilage, you can see that it's no longer smooth, it's very abrasive. So yeah, this is how I actually ended up watching the video of the hip surgery. So when we're talking about total hip replacement, we know that the hip is the largest load-bearing joint, and it's lined with that articular cartilage. If we get damage to that cartilage, we can have extreme pain. So this is a process that we go to replace that socket with this kind of with this replacement ball joint. Is that the upper, actually makes me feel bad reading it out, but the upper leg bone, the femur, is separated from the hip socket. The damaged head is removed, so they'll saw that off and get rid of it. They use a reamer to prepare the socket, so they'll insert the reamer to cut out not cut out, but shape an area for the socket to enter. A file is then used to create a tunnel in the femur for that insertion of the prosthetic femoral stem. And then the hip and socket prostheses are cemented in place. So the example here is on D&E, these two bottom images, where the hip and socket are cemented in place and connected together. So it's a fairly intense surgery. And then we can also have a similar kind of case with the total knee replacement. So the knee joint as well is lined with this articular cartilage. So if you have osteoarthritis or injury, you can damage that. And obviously, that causes lots of discomfort and pain. So what they have is two components in there. They have a femoral component, which is inserted into the femur, and this tibial component, which goes into the tibia. And they have a plastic spacer in between. Now, the plastic spacer that they use in between most commonly now is the ultra high molecular weight polyethylene. But the problem is that over time, those polyethylene spacers can start to wear down and break down. So often you may have to do a replacement of that plastic spacer. Now, actually, these the replacement, the joint replacements have a good success rate. So in the USA, there's around 250,000 hip replacements and 320,000 knee replacements done annually. Obviously, that's expected to increase by 25% by 2030. And I don't think that's due to the number of people that have taken up jogging. I think that's just because we've actually got an aging population. So that hip replacement, the average age is around about 66 years old. 57% are women. So after 10 years, you can see that there is a 90% retention in the function of that joint. After 20 years, that dips another 10% to 80%, and after 30 years, we see kind of 50%. So actually, these things are functioning for a long time. Now, the primary, so the failure is primarily due to the implant loosening, which is due to bone loss. So we can have stress shielding. So how do you think stress shielding causes the loosening of that implant?
As you get bone loss, the bone kind of separates away from the implant, so it's able to move around.
Correct. Yeah. So as we get bone loss in there around that implant, it causes it to separate. So I'm just going to write in there bone loss around implant. But one of the other ways that you get it is the buildup of this kind of wear debris. So as things such as the spacers start to wear, you can get a buildup of debris in the joint as well. Let me write that out a little bit neater for you. And obviously, in any of these circumstances, you're going to need some kind of revision surgery in there to fix it. So as we've seen before, instead of using ceramics, we're opting to use this ultra high molecular weight polyethylene as these acetibular cups. So that's in the hip replacements. So there's billions and trillions of particles that come off of those cups every step. Now, obviously, the wear rate seems fairly low, so it's actually 0.1 of a millimeter a year. But the issue with that is that because it's such a fine area, that even a wear rate of 0.1 millimeters per year is going to cause some issues. So what happens is that you get this migration to the bone, which causes osteolysis, which is rapid bone loss, which then causes implant loosening. You can have an immune response to wear particles as well. So you can have inflammation of the joint that occurs because of these particles being released. And then you also have bone modeling, the balance of bone modeling, which is upset. The percentage of osteoclasts, which are bone reabsorbing, increases. And the potential, the number of osteoblasts, which are bone building, decreases. So essentially what we're saying is that loosening can cause the implant to be removed, but even in worse situations, that loosening can also cause femoral fracture. So not only have you got a hip replacement in there, you've got the potential to have a fracture of your femur as well, which is a particularly dangerous place to have a fracture. I think actually the femur generates most of the red blood cells in the body, so you can actually bleed out from those things. So it's not a nice accident to have. A steeper position, when they implant in a steeper position, that indicates migration. So they have this eccentric positioning of the femoral head, which indicates the wear of that acetibular cup. So you can see there is a slight difference in the shading, which is caused by wear there. Now we can improve it. So we can improve the wear resistance of that ultra high molecular weight polymers. The first way to do it is to use gamma irradiation in an air-free environment. So that improves cross-linking. If we improve the cross-linking density, we can elicit some improved wear resistance. We can impact that process. So 90%. So when we do that, when we use a high cross-linked polyethylene, we can demonstrate that we have a 90% reduction in wear at 5 million cycles. So that's 5 years of normal wear based on hip simulator studies. So I don't know how much these hip simulator studies, the in vivo environment, but what they're essentially showing is that when they've cycled this process to wear down the polyethylene, is that it wears at a much lower rate. Okay, so I think we've made it to the end for today, so we'll carry this one on in the next lecture. Please look out for, so tonight I'm going to post a homework assignment which will be due next Friday, but it's just to go over some of the material that we've covered since lecture 9, which now seems a while ago, but it's not that long. There's some material in there, but that'll be due in on next Friday, but I'll give you all the information over campus.
We need to fill it.
Oh yeah, cross-linking. Not used to writing now. Okay, good. Well, I hope you all have a good weekend. Enjoy the overcast weather.
Dr. Marbet, I have a question about the bond plates.
Yes.
So it says that when using the metals for the bond plates, the metal modulus, the storage, like elastic modulus, is much higher than that of the natural tissues.
Yes.
So it says that polymer can be used instead of metal.
Oh yeah, so the polymer allows us to match up more better probably
Mhm.
to the elastic modulus of what we're trying to restore. So it's not all materials, but certainly for like blown plates and stuff, you'll see there is polymer versions of those as well.
Okay, thank you.
No problem.